Right now, there is something in the universe so incomprehensibly massive that if you could see it in its totality, every calculation we've built about reality would shatter. You cannot see it. You cannot touch it. But the James Webb Space Telescope just measured it, and what it revealed is forcing scientists to rewrite the boundaries of existence itself. Prepare yourself. We begin. Before we journey into the abyss, hit that subscribe button and turn on notifications, because what you're about to witness will change how you see the night sky forever. Look up tonight. Those stars you see, those tiny pinpricks scattered across the darkness. Webb just proved that for every star visible to your naked eye, there are roughly 10 trillion others hidden in the cosmic shadows. 10 trillion. That number alone should stop you cold. But here's the part that scientists didn't expect. When Webb turned its infrared gaze toward what we thought were empty patches of void, the deepest, darkest corners of observable space, it found galaxies. Not dozens, not hundreds. Thousands upon thousands of ancient galaxies glowing in wavelengths our eyes will never perceive, each one containing hundreds of billions of stars, floating in regions of space we assumed were barren. These galaxies have been there all along. We just couldn't see them until now. But the emptiness isn't the worst part. The James Webb Space Telescope sits 1.5 million kilometers from Earth, orbiting a gravitational balance point called Lagrange 2. It's so far out that if something breaks, no astronaut can reach it to fix it. No second chances. Yet from that frozen position, negative 233 degrees Celsius in the Yongju shadow of its sun shield, Webb peers backward through time itself. Its 18 gold-coated beryllium mirrors, each polished to within 1/10,000th the width of a human hair, collect ancient photons that have traveled for over 13 billion years. Light that left distant galaxies when the universe was barely 300 million years old. To put that in perspective, imagine the entire history of the cosmos as a single year. Webb is showing us what happened on January 2nd, and those first glimpses revealed something we were not prepared to see. Picture this. You're told the universe began in chaos, a violent, formless soup of energy that took billions of years to cool, condense, and organize into the first primitive stars. Those early stars would have been small, crude, unstable. This is what every model predicted. This is what the textbook said. Then Webb looked at the infant universe and found galaxies that were already massive, already structured, already spinning with elegant spiral arms and glowing with organized starlight. Galaxies that, according to our understanding of physics, should not exist yet. Some of these ancient structures contain stellar masses equivalent to billions of suns, fully formed in a cosmic eye blink. Scientists call this the impossible early galaxy problem, which means one of our foundational assumptions is wrong. Think of it like finding a skyscraper in ancient ruins. You excavate a site from 5,000 years ago, expecting stone tools and pottery shards. Instead, you uncover steel beams, elevator shafts, and electrical wiring. That's the level of temporal impossibility we're confronting. These galaxies assembled faster than our equations allow. Either gravity worked differently in the early universe, or dark matter clumped together in ways we don't understand, or something even stranger was at play. The data points to something we didn't want to see. Time itself may not have flowed the way we assumed. Now flip it around. If these galaxies formed too quickly in the past, what does that tell us about the future? Webb didn't just shatter our models of cosmic infancy. It also measured something happening right now in the present-day universe that contradicts everything we thought we knew about expansion. Scientists have been measuring the rate at which the universe is expanding for decades. It's called the Hubble constant. The number should be fixed. One universe, one expansion rate, one constant. But when Webb measured the distances to certain types of stars called Cepheid variables, stars that pulse with clockwork regularity and serve as cosmic yardsticks, the calculated expansion rate didn't match. Not by a little. By enough to be statistically impossible if our understanding is correct. The problem is, we can't test it directly. The Hubble tension, as it's known, has persisted for years. Ground-based telescopes measured one value. The Hubble Space Telescope measured something slightly different. Scientists hoped Webb would resolve the conflict. Instead, Webb's measurements confirmed Hubble's numbers with even greater precision. The local universe, measured by nearby stars, is expanding roughly 8% faster than the distant universe measured by the cosmic microwave background, the afterglow of the Big Bang itself. 8% doesn't sound catastrophic until you realize what it implies. Either we're measuring something wrong, which seems unlikely given the precision of Webb's instruments, or the universe is not uniform. There are regions where space itself is stretching at different rates, and that should not be possible under general relativity, unless the fabric of reality has a flaw. Hold that thought. We need to talk about what Webb discovered when it looked at something even stranger than galaxies or expansion rates, something that exists right now, scattered across the universe in numbers so vast they defy comprehension. Rogue planets. Not planets orbiting stars. Planets adrift in the interstellar void, untethered to any solar system, wandering through the frozen darkness alone. Webb's infrared vision allowed it to detect the faint heat signatures of these orphaned worlds for the first time at scale. And the numbers are staggering. Early estimates suggest there may be trillions of rogue planets in our galaxy alone, possibly more rogue planets than stars. Think about what that means for a moment. These planets were born in solar systems, formed from the same swirling disks of gas and dust that created their host stars. Then something violent happened. A gravitational slingshot, a near miss with another star, a sudden lurch in the orbital dance, and they were flung outward, cast into the eternal night, traveling at speeds of tens or even hundreds of kilometers per second, with no sun to warm them, no light to guide them. Their surfaces, if they have solid surfaces, are colder than anything you can imagine. -240 degrees Celsius, -250. So cold that gases freeze solid, that methane becomes ice harder than granite, that the only heat comes from the residual warmth of their molten cores slowly dying over billions of years. But some of them might not be dead. Webb detected infrared emissions from certain rogue planets that suggest geological activity. Volcanic eruptions powered not by a sun, but by tidal forces from massive moons, or by the decay of radioactive elements deep underground. On Earth, we have ecosystems that thrive in absolute darkness, clustered around hydrothermal vents on the ocean floor, feeding on chemical energy instead of sunlight. If a rogue planet has a thick atmosphere to trap its internal heat, if it has liquid water beneath a frozen crust, it could theoretically harbor life. Life that never sees a star. Life that evolves in permanent crushing darkness. And if rogue planets outnumber stars, the sheer probability suggests such worlds might be common. We thought we understood where to look for life. We were looking in the wrong place. Now zoom out. Forget individual planets. Forget even galaxies. Webb has been mapping the large-scale structure of the universe, the cosmic web, a filamentary network of galaxy clusters connected by tendrils of dark matter spanning hundreds of millions of light years. From a distance, the universe resembles a neural network, a vast organic lattice with dense nodes connected by gossamer threads. And in between those threads, there are voids, not just empty space. Voids so enormous they dwarf anything we can conceptualize. The Buddha's void, for example, is roughly 330 million light-years across. If our Milky Way galaxy were located at the center of the Buddha's void, we would not have discovered other galaxies until the 1960s. Think about that. Entire civilizations could arise, develop astronomy, build telescopes, scan the heavens, and see nothing but darkness for thousands of years. And this is where it turns strange. Webb's observations reveal that these voids are not truly empty. There's something in them. Not galaxies, not stars, but a faint glow. A barely detectable haze of light that has no obvious source. Scientists call it the cosmic optical background, and it's been a mystery for years. Some of that glow comes from distant, faint galaxies that our instruments can't resolve individually. But when you subtract all the known sources, there's still light left over. Orphan light. photons traveling through the universe with no clear origin. One hypothesis suggests this light comes from stars that were ripped out of their galaxies during collisions and now drift freely through intergalactic space, solitary suns wandering the voids. Another hypothesis is darker. The light might be a remnant of something that happened in the universe's first moments, something we don't yet understand. Which brings us to the question no one wants to ask. What if the voids aren't empty by accident? Every structure in the universe exists because of gravity. Gravity pulls matter together. It forms stars, planets, galaxies, clusters, but gravity is only an attractive force. It has no mechanism to push things apart, to carve out vast empty regions on such scales. The standard explanation is that the voids formed naturally during the universe's infancy, regions where matter density was slightly lower, so gravity pulled material away toward denser regions, leaving bubbles behind. But Webb's data shows that some voids have sharper boundaries than the models predict. Edges that are too defined, too geometric, almost as if something is actively preventing matter from crossing into these regions. And the data points to something we didn't want to see. Dark energy, the mysterious force driving the accelerated expansion of the universe. We know it exists because we can measure its effects, but we have no idea what it is. No particle has been detected, no field has been confirmed. It's purely a placeholder term for whatever is causing space itself to stretch faster over time. Standard cosmological models assume dark energy is uniform, a constant background pressure distributed evenly throughout the universe. But what if it's not uniform? What if dark energy is stronger in the voids, actively repelling matter, creating these vast empty bubbles? If that's true, it would mean dark energy is not a cosmological constant. It's a dynamic field that varies in strength across space. And that changes everything. Because at the center of this mystery, something waits. Let's shift perspective. Away from the voids, back toward the densest structures in the cosmos. Webb recently imaged a galaxy cluster known as SMACS 0723, one of the deepest and most detailed images of the distant universe ever captured. The cluster itself is roughly 4 billion light-years away, but its gravity is so immense that it bends the fabric of space-time, acting as a natural magnifying glass. This effect, called gravitational lensing, allows Webb to see galaxies far behind the cluster, galaxies that would otherwise be too faint and distant to detect. In that single image, there are thousands of galaxies, stretching back over 13 billion years, layered like archaeological strata. Each one a civilization of stars, many of which have already died, their light only now reaching us after traversing the expanding void. But the real shock is what comes next. When astronomers analyzed the lensed galaxies in that image, they found objects that should not be visible. Galaxies so distant, their light has been redshifted beyond what the previous generation of telescopes could detect. Redshift is a measure of how much the universe has expanded since the light was emitted. The higher the redshift, the farther back in time you're looking. Hubble could reach redshift values around 11 or 12. Webb has detected galaxies with redshift values exceeding 13, 14, even approaching 15. These are galaxies from the universe's first 400 million years. And they are not small. They are not primitive. Some of them are already shining with the light of billions of stars. We thought we understood galaxy formation. We were wrong. According to the Lambda cold dark matter model, the prevailing framework for cosmic evolution, galaxies grow hierarchically. Small structures form first, then merge over billions of years into larger ones. The first galaxies should have been tiny, irregular, low mass. But Webb is seeing massive organized galaxies appearing far too early in cosmic history. One galaxy cataloged as CEERS 93501 has a redshift of approximately 16.7. If that measurement holds, the galaxy's light was emitted just 230 million years after the Big Bang. To put that in context, that's roughly 1.7% of the universe's current age. Imagine a human infant, 2 weeks old, with the cognitive abilities of a 30-year-old. That's the level of developmental impossibility we're observing. So what does that feel like? Imagine you're a detective working a case. You have a clear timeline. The crime happened at midnight. The evidence should reflect that. Then you find a witness who saw the suspect at 10 p.m., 2 hours before the crime could have occurred. Impossible. Either your timeline is wrong, or the witness is lying, or something fundamental about how you understand time is flawed. That's where astronomers are now. The evidence is piling up. The galaxies are there. The measurements are precise. But the timeline doesn't fit. Some scientists are suggesting we need to revise the age of the universe. Others propose that dark matter behaved differently in the early cosmos, clumping together faster, seeding galaxy formation earlier than expected. A few are even questioning whether the Big Bang model itself needs adjustment. But the emptiness isn't the worst part. Webb's discoveries extend beyond galaxies. It has also been studying exoplanet atmospheres in unprecedented detail, analyzing the starlight that filters through alien skies as planets transit in front of their host stars. The chemical fingerprints revealed in that light tell us what those atmospheres are made of: water vapor, carbon dioxide, methane, sulfur compounds. On a planet called K218b, a super-Earth orbiting a red dwarf star 120 light-years away, Webb detected something startling: dimethyl sulfide, a molecule that, on Earth, is produced almost exclusively by biological processes, specifically by phytoplankton in the ocean. No known abiotic process generates significant quantities of dimethyl sulfide. Does that mean there's life on K218b? Not necessarily. The detection is tentative, and scientists are being appropriately cautious. There could be unknown geological or chemical processes that produce dimethyl sulfide without biology. But the possibility is real enough that follow-up observations are already being planned. K218b is classified as a Hycean world, a hypothetical type of planet with a hydrogen-rich atmosphere and a global liquid water ocean beneath. If life exists there, it would be adapted to conditions radically different from Earth: higher pressure, lower light, an atmosphere that would be toxic to us. But life, as we've learned from extremophiles here on Earth, is astonishingly adaptable. It thrives in boiling acid, in frozen Antarctic lakes, in the crushing darkness of the deep ocean. If life can emerge on one Hycean world, it can emerge on others. And Webb is finding that Hycean planets may be common. We thought we were alone. The data suggests otherwise. But there's something else. Something Webb detected that has nothing to do with planets or galaxies or expansion rates. Something that exists outside the visible universe entirely, inferred only through its gravitational effects. Dark matter. The invisible scaffolding that holds galaxies together, that outweighs all the normal matter in the universe by a factor of approximately 5-to-1. We know dark matter exists because galaxies spin too fast. The visible stars and gas don't have enough mass to generate the gravity needed to hold the galaxy together at those rotation speeds. There must be something else, something we can't see, providing the additional mass. For decades, scientists have tried to detect dark matter particles directly. Every experiment has failed. No signal, no interaction, nothing. Which means one of our assumptions is wrong. Webb's observations are now adding a new layer to the mystery. By studying the gravitational lensing effects of galaxy clusters, Webb can map the distribution of dark matter with extraordinary precision. And what it's finding is unsettling. Dark matter doesn't distribute itself evenly. It clumps in specific patterns, forming filaments and halos that don't quite match what simulations predict. In some regions, the dark matter seems denser than it should be. In others, more diffuse. There are clumps within clumps, subhalos within halos, a fractal complexity that suggests dark matter isn't a single type of particle. It might be a whole ecosystem of particles, interacting with each other through forces we don't understand. Or it might not be particles at all. Some physicists are proposing that what we call dark matter is actually a modification of gravity itself. That Einstein's general relativity, while extraordinarily accurate at human scales and even at the scale of the solar system, breaks down at galactic scales. Modified Newtonian dynamics, or MUND, is one such theory. It suggests that gravity behaves differently when accelerations are extremely small, as they are in the outer regions of galaxies. Under MOND, you don't need dark matter. The extra gravitational pull comes from the modified law of gravity itself. But MOND has problems. It struggles to explain the cosmic microwave background, the distribution of galaxy clusters, and the precise lensing effects Webb is now measuring. So if dark matter isn't particles and it isn't modified gravity, what is it? The problem is we can't test it directly. Dark matter interacts with ordinary matter only through gravity. It doesn't emit light, doesn't absorb light, doesn't scatter electrons, doesn't do anything except pull. If a dark matter particle passed through your body right now, you would never know. Trillions of them might be streaming through Earth every second, and we'd be oblivious. The only way to detect them is to build incredibly sensitive experiments deep underground, shielded from cosmic rays, and wait for a dark matter particle to, by sheer chance, collide with an atomic nucleus. And after decades of waiting, we have detected nothing. Either dark matter particles are even more elusive than we thought, or we're looking for the wrong thing entirely. Hold that thought. We need to talk about black holes. Not the stellar mass black holes formed from collapsing stars, the supermassive ones. The monsters lurking at the centers of galaxies, with masses millions or even billions of times that of our sun. Webb has been studying these objects with unprecedented clarity, and the findings are deeply troubling. According to standard models, supermassive black holes grow slowly over billions of years, feeding on gas and stars, gradually accumulating mass through accretion and mergers. But Webb has found supermassive black holes in the early universe, less than 1 billion years after the Big Bang, that are already billions of solar masses. Far too massive to have grown through conventional processes in the time available. It's the galaxy problem all over again, but worse. One black hole, found in a quasar designated J0313-1806, has a mass estimated at 1.6 billion solar masses. The light we're seeing from this quasar was emitted when the universe was only 670 million years old. Do the math. For a black hole to reach that mass in that time frame, it would need to feed continuously at or near the Eddington limit, the maximum rate at which a black hole can accrete matter before radiation pressure blows away the infalling gas. And even then, the numbers barely work, unless the black hole started much larger than it should have, which leads to a disturbing hypothesis. What if some black holes didn't form from collapsing stars? What if they were born directly from the Big Bang itself? These are called primordial black holes. In the first fraction of a second after the Big Bang, the universe was unimaginably dense and hot. Small fluctuations in density could have caused regions to collapse directly into black holes, bypassing the need for stars entirely. These primordial black holes could have any mass, from microscopic to millions of solar masses, depending on the size of the density fluctuation. And if they formed early enough, they could serve as the seeds for supermassive black holes, giving them a head start. The problem is, no one has ever detected a primordial black hole. They remain theoretical, but Webb's observations are making them harder to ignore. If supermassive black holes exist in the infant universe and they can't have grown from stellar remnants, then primordial black holes might be the only explanation. And here's where it turns truly strange. Some scientists are now suggesting that primordial black holes could be dark matter. Not all of it, but a significant fraction. If the early universe produced enough primordial black holes in the right mass range, they could account for the missing mass we've been searching for. They would be invisible, check. They would interact only through gravity, check. They would clump in specific patterns, forming the halos and filaments we observe, check. And they would explain why decades of particle detector experiments have found nothing. Because there are no particles, just black holes. Ancient, invisible, scattered throughout the cosmos like seeds. The idea is controversial, and there are observational constraints that rule out certain mass ranges. But it's gaining traction, because at the center of this, something waits. Let me give you an analogy that makes this feel real. Imagine you're standing in a dark room. You know there's furniture in the room because you keep bumping into it, but you can't see any of it. That's dark matter. Now imagine that instead of furniture, the room is filled with invisible black holes, each one warping space around it, creating gravitational traps you can't perceive until you're already falling. That's the universe Webb is revealing. A cosmos far more dangerous, far more complex than we imagined, and we've only just begun to map it. Now zoom out one more time. All of this, the galaxies, the dark matter, the supermassive black holes, the rogue planets, the voids, all of it exists within the observable universe. A sphere roughly 93 billion light-years in diameter, centered on Earth. That's as far as light has been able to travel since the Big Bang, accounting for the expansion of space. Beyond that boundary, there is more universe. We just can't see it. The light from those regions hasn't had time to reach us yet. But here's the thing. The observable universe is almost certainly a tiny fraction of the total universe, possibly an infinitesimal fraction. Depending on the shape and topology of space, the universe could be infinite, literally infinite, extending forever in all directions. And this is where it turns strange. If the universe is infinite and the distribution of matter is roughly uniform on large scales, then every possible arrangement of particles must exist somewhere, not just once, infinitely many times. There would be infinitely many copies of Earth, infinitely many copies of you, reading these exact words. Some would be identical down to the quantum level. Others would differ in tiny details. One where you chose tea instead of coffee this morning. One where you never learned to read. One where Earth never formed. The probabilities become certainties in an infinite universe. Everything that can happen does happen, infinitely. We thought we understood our place in the cosmos. We were wrong. This is not science fiction. This is a logical consequence of cosmic inflation, the theory that the universe underwent a brief period of exponential expansion in its first fraction of a second. Inflation stretched space so rapidly that regions which were once in causal contact, able to exchange information, were driven beyond each other's observable horizons. What we see as the observable universe is just one patch of a vastly larger, possibly infinite inflated space. And if inflation happened once, it could happen elsewhere. Other patches of space could inflate, creating bubble universes, each with its own laws of physics, its own constants of nature, its own history. This is the multiverse hypothesis. And while it remains speculative, it's increasingly difficult to avoid if inflation is correct. The problem is, we can't test it directly. If other universes exist beyond our cosmic horizon, we have no way to observe them. No signal can travel faster than light, and space itself is expanding faster than light at those distances. We are causally disconnected, trapped in our own bubble. The only potential evidence might come from subtle imprints in the cosmic microwave background, faint anomalies that could indicate a collision between our universe and another during the inflationary period. Webb isn't designed to study the microwave background. That's the domain of missions like Planck, but its precision measurements of large-scale structure can constrain inflationary models, narrowing the range of possibilities. And the data points to something we didn't want to see. The cosmic microwave background is almost perfectly uniform. Almost. There are tiny fluctuations, temperature variations of 1 part in 100,000, that represent the seeds of all structure in the universe. Regions that were slightly denser became galaxies. Regions that were slightly less dense became voids. But there's an anomaly, a feature called the cold spot, a region of the sky where the microwave background is slightly colder than it should be, about 70 microkelvins colder to be precise. It's larger than expected, and its existence has been confirmed by multiple observations. Standard inflationary models predict fluctuations, but not this large. One explanation is that it's just a statistical fluke, a rare but a loud fluctuation. Another explanation is that it's the imprint of a collision with another universe. But there's a third explanation, and it's darker. The cold spot aligns with one of the largest supervoids ever discovered, a region roughly 1.8 billion light-years across where galaxy density is significantly lower than average. Supervoids can cause the microwave background to appear colder through a process called the integrated Sachs-Wolf effect, but the magnitude doesn't quite match. The void isn't large enough or empty enough to fully explain the cold spot, unless something else is happening inside that void, unless the properties of space there are subtly different, unless dark energy is stronger in that region, actively repelling matter and creating a bubble of altered physics. If that's true, the cold spot isn't an anomaly. It's a window into a different regime of reality, a place where the laws of nature deviate from the norm. Picture this. You're drifting in the ocean. The water around you is calm, familiar. Then you cross an invisible boundary, and suddenly the water feels different, thicker, colder. The pressure changes. You realize you've entered a region where the ocean itself has different properties. That's what supervoids might represent. Domains within the universe where dark energy or some other field has settled into a different state. And if such domains exist, they could expand. They could collide. They could merge. The universe might not be a uniform expanse. It might be a patchwork of regions, each with slightly different physics, separated by boundaries we can't see. Which brings us to the question no one wants to ask. What happens when one of those boundaries reaches us? Now flip it around. Instead of looking outward at the largest structures, let's look inward at the smallest. Quantum mechanics governs the behavior of particles at subatomic scales, and it's deeply weird. Particles can exist in multiple states simultaneously until observed. They can tunnel through barriers that classical physics says are impenetrable. They can become entangled, sharing information instantaneously across arbitrary distances. And here's the kicker. Quantum mechanics and general relativity, the two pillars of modern physics, are fundamentally incompatible. General relativity describes gravity as the curvature of space-time, a smooth, continuous fabric. Quantum mechanics describes everything else through discrete particles and probabilistic wave functions. The two theories work beautifully in their respective domains, but when you try to combine them, the math breaks down. We've known this for decades, but we ignored it because the regimes where both theories matter simultaneously are extreme. Black hole singularities, the Big Bang, places we can't probe experimentally. But Webb is now giving us data from the early universe, from regions where quantum fluctuations seeded the formation of galaxies, where the universe was small enough that quantum effects and gravitational effects were both significant. And the data is revealing tensions, small discrepancies between what quantum field theory predicts and what we observe. Nothing conclusive yet, but enough to make physicists nervous. Because at the center of this, something waits. String theory is one attempt to unify quantum mechanics and gravity. It proposes that the fundamental constituents of reality are not point-like particles, but one-dimensional strings vibrating in higher dimensional space. Different vibration modes correspond to different particles. The graviton, the hypothetical particle that mediates gravity, is just one vibration mode. String theory is mathematically elegant and has the potential to explain everything, but it has a problem. It makes almost no testable predictions. The energy scales required to probe string theory directly are far beyond anything we can achieve with particle accelerators. And it requires extra dimensions, up to 10 or 11 depending on the formulation, dimensions that are supposedly curled up so small we can't detect them. Unless those dimensions aren't so small after all. Some versions of string theory allow for large extra dimensions, dimensions that extend macroscopically but are hidden from us because ordinary matter is confined to a three-dimensional brain, a membrane embedded in the higher dimensional space. Gravity, however, can propagate through all dimensions. If large extra dimensions exist, gravity should become stronger at short distances, deviating from Newton's inverse square law. Experiments have looked for this effect and found nothing, but the constraints are weak. We've only tested gravity down to scales of around 50 micrometers. Smaller than that, we don't know. And if extra dimensions exist, they could have cosmological implications. Dark energy, for instance, might be leakage of gravity into extra dimensions. Dark matter might be particles confined to a parallel brane, invisible to us but still exerting gravitational influence. We thought the universe had 3 dimensions of space and 1 of time. The data suggests otherwise. Webb can't directly detect extra dimensions, but it can measure the effects they might have. If dark energy is related to extra dimensions, its strength should change as the universe expands, and that change should be visible in the redshift dependence of supernovae and other distance indicators. If primordial black holes formed from density fluctuations in higher dimensional space, they might have characteristics that differ from black holes formed from collapsing stars. These are subtle effects, requiring precise measurements and careful analysis, but they're within Webb's capabilities. And as more data accumulates, as more galaxies are cataloged, more spectra analyzed, more lensing events studied, the constraints will tighten. We'll either rule out large extra dimensions or find evidence for them. Either outcome is profound. Hold that thought. Let's return to something more immediate, something happening right now in our own galaxy. Star formation. The process by which clouds of gas and dust collapse under gravity, heat up, and ignite nuclear fusion, giving birth to new stars. We've studied this process for decades using visible light telescopes, but visible light can't penetrate the thick dust clouds where stars are born. Infrared light can. And Webb's infrared vision is revealing the stellar nurseries of the Milky Way in unprecedented detail. One target, the Carina Nebula, a massive star-forming region about 7,600 light-years away, has been imaged by Webb with stunning clarity, and what Webb found is unsettling. Inside the nebula, there are structures, pillars of gas and dust shaped by the intense radiation from nearby massive stars. These pillars are being eroded, sculpted by ultraviolet light and stellar winds, and within them, new stars are forming. But the process is more violent than we thought. The radiation doesn't just erode the pillars, it compresses them, triggering runaway collapse in some regions while dispersing others entirely. It's a feedback loop. Massive stars form, they blast their surroundings with radiation. That radiation triggers the formation of more stars, some of which become massive themselves and continue the cycle. Eventually, the most massive stars explode as supernovae, enriching the gas with heavy elements and sometimes triggering another wave of star formation. It's beautiful and destructive in equal measure. But here's what's strange. Webb's images show jets, narrow beams of gas shooting out from the cores of forming stars at speeds of hundreds of kilometers per second. These jets are powered by the star's rotation and magnetic fields, and they carry away angular momentum, allowing the star to continue accreting material without spinning itself apart. We knew jets existed, but we didn't know how common they were. Webb is finding them everywhere. In almost every star-forming region observed, there are jets, dozens of them, hundreds, and they're not random, they're aligned, not perfectly, but statistically more aligned than random chance would allow. Jets from different stars, separated by light years, pointing in roughly the same direction. What could cause that? One possibility is that the molecular cloud itself, the giant structure from which all these stars are forming, has a preferred magnetic field direction. As the cloud fragments and collapses into individual stars, each star inherits a component of that field, and the jets align with the field lines. That's the standard explanation. But Webb's precision is revealing that the alignment persists across larger scales than the magnetic field coherence length should allow. It's as if there's an organizing principle we don't understand, a hidden order in the chaos of star formation. Some researchers are speculating about primordial magnetic fields, fields that date back to the early universe and have survived to the present day, threading through galaxies and influencing structure formation on all scales. And the data points to something we didn't want to see. Magnetic fields are everywhere in the universe. Galaxies have them. Galaxy clusters have them. Even the intergalactic medium has faint magnetic fields threading through the voids. Where did they come from? The dynamo mechanism can amplify weak seed fields into strong fields over time, but it requires a seed. You can't create a magnetic field from nothing. Standard models assume the seeds were generated by the first stars or by turbulent motions in the early universe, but the observations suggest the fields are too strong, too widespread to have formed that way, unless they're primordial. Unless they were baked into the universe during inflation, quantum fluctuations of electromagnetic fields that got stretched to macroscopic scales and frozen in as the universe expanded. If that's true, magnetic fields are a fundamental feature of the cosmos, not an afterthought. Now zoom out again, away from star formation, back to the large-scale structure. The cosmic web is held together by dark matter, but the visible matter, the gas and stars, flows along the dark matter filaments like water through channels. And as that gas flows, it heats up. Friction, compression, gravitational infall all generate heat. By the time the gas reaches a galaxy cluster, it's been heated to millions of degrees, hot enough to emit X-rays. But it's also hot enough that it should evaporate, should escape the cluster's gravity and disperse into the intergalactic medium. That doesn't happen. Something is holding it in place. That something is dark matter. Again. The galaxy cluster acts as a laboratory for studying dark matter. The visible gas traces the gravitational potential well created by the dark matter halo. By measuring the temperature and density of the gas, we can infer the shape and depth of the potential well, and from that, we can infer the distribution of dark matter. Webb's infrared observations complement X-ray data from missions like Chandra, providing a multi-wavelength view of these massive structures. And what we're seeing is that dark matter halos are not smooth. They have substructure, smaller halos within halos, clumps and streams of dark matter that survived the mergers that form the cluster. This substructure is a prediction of the standard cold dark matter model, but the details matter. Too much substructure, and the model is wrong. Too little, and it's also wrong. Webb's lensing measurements are now precise enough to detect individual dark matter subhalos, even if they contain no visible matter at all. When light from a distant background galaxy passes through a cluster, the dark matter subhalos perturb the light path, creating tiny distortions in the lensed image. By analyzing these distortions, astronomers can count the subhalos and measure their masses, and the preliminary results are intriguing. There seem to be fewer low-mass subhalos than simulations predict. This is known as the missing satellites problem, and it's been a thorn in the side of the cold, dark matter model for years. Various solutions have been proposed. Maybe the low-mass halos are there, but they failed to form stars, so we can't see them. Maybe dark matter is warmer than we thought, suppressing small-scale structure. Maybe there's dark matter self-interaction, collisions between dark matter particles that smooth out the distribution. Or maybe the simulations are wrong. Simulations of cosmic structure formation are incredibly complex. They have to account for dark matter, gas dynamics, star formation, supernova feedback, black hole growth, magnetic fields, cosmic rays, and more. Each process affects the others in non-linear ways, and small changes in the input parameters can lead to large differences in the output. The simulations are tuned to match observations of the present-day universe, but that doesn't guarantee they're correct at all scales and all times. Webb is now probing regimes that the simulations were never calibrated for. The early universe, the first galaxies, the first stars, and the mismatches are piling up. The galaxies are too massive. The black holes are too massive. The star formation is too efficient. Either we're missing key physics, or our initial conditions are wrong, because at the center of this, something waits. Let me give you an analogy. Imagine you're watching a time-lapse video of a city being built. You see the first foundations laid, the first buildings erected, the infrastructure expanding. Based on the early frames, you predict how the city will look decades later. Then you fast forward and discover the city looks nothing like your prediction. The buildings are taller, the layout is different. There are structures you didn't account for. Either your model of urban development is flawed, or something happened during the time lapse that you didn't see. An influx of resources, a change in planning policy, an external intervention. That's where cosmology is right now. We have a model of cosmic development, lambda CDM, and it works remarkably well for the late universe. But when we look at the early frames, the data doesn't fit. Something happened that we didn't account for. And this is where it turns truly strange. One of the most radical proposals is that the constants of nature were different in the early universe. The fine structure constant, which governs the strength of electromagnetic interactions, the gravitational constant, the mass of the electron. These are supposed to be constants, unchanging across time and space. But what if they're not? What if they evolved as the universe expanded, settling into their present values only after the first billion years or so? This idea, called varying constants cosmology, is highly speculative, but it's not ruled out by observation, and it would explain a lot. If gravity was stronger in the early universe, structures would form faster. If the fine structure constant was different, stellar physics would change, affecting nucleosynthesis and the formation of the first stars. We thought the laws of physics were universal. The data suggests otherwise. Testing this idea is difficult. You need to measure the values of constants in the distant past and compare them to the present. One way to do this is to study the spectra of distant quasars. The absorption lines produced by gas clouds along the line of sight depend on the fine structure constant. If the constant was different when the light was emitted, the absorption lines would be shifted by a tiny amount. Some studies have claimed to detect such shifts, but the results are controversial and not widely accepted. Webb spectra are more precise than anything we've had before, and as more quasar observations accumulate, we'll be able to place tighter constraints on varying constants. If the constants are truly constant, we'll confirm that. If they're not, we'll have to rewrite fundamental physics. Either outcome is profound. Now let's talk about something closer to home. Our own galaxy, the Milky Way. It's a barred spiral galaxy, roughly 100,000 light-years across, containing between 200 billion and 400 billion stars. At the center, there's a supermassive black hole called Sagittarius A star, with a mass of approximately 4 million solar masses. We know a lot about the Milky Way because we're inside it, but that also makes certain observations difficult. You can't see the shape of the forest when you're standing among the trees. Webb is now helping us map the Milky Way's structure in ways that weren't possible before, particularly its infrared emission, which penetrates the dust that obscures visible light. And what Webb is revealing is strange. The Milky Way's disk is not smooth. It's warped, twisted like a vinyl record left in the sun. The warp becomes more pronounced toward the outer edges, where the gravitational influence of the central bulge is weaker. One explanation is that the Milky Way is interacting with its satellite galaxies, the Magellanic Clouds, and their gravity is pulling on the outer disk, distorting it. But the warp's geometry doesn't quite match what you'd expect from that interaction. Another possibility is that the Milky Way's dark matter halo is not symmetric. If the halo is elongated or tilted relative to the disk, it could cause the warp. Webb's observations of star-forming regions in the outer disk are providing new data on the warp's shape and evolution, and the picture is becoming clearer, but also more complex. But the warp isn't the strangest thing. There's also the Fermi bubbles, two enormous structures of high-energy gamma rays extending above and below the galactic center, each roughly 25,000 light-years tall. They were discovered in 2010 by the Fermi Gamma Ray Space Telescope, and their origin remains a mystery. One hypothesis is that they're the remnants of a massive outburst from Sagittarius A star, a period of intense accretion millions of years ago when the black hole was actively feeding. Another hypothesis is that they're powered by stellar winds and supernovae from the central star-forming region. Webb can't directly observe gamma rays, but it can study the gas and dust in the region, looking for signs of past activity. And what it's finding suggests that both mechanisms may have contributed. There's evidence of recent star formation in the galactic center, and there are also hints of structures that could be remnants of jets from the black hole. Which raises the question, is Sagittarius A star still active? Right now, Sagittarius A star is relatively quiet. It accretes a small amount of gas, emits some radiation, but nothing dramatic. However, there's a massive cloud of gas called G2 that passed close to the black hole in 2014. Astronomers expected a fireworks show. The cloud should have been torn apart by tidal forces, heated to extreme temperatures, and consumed by the black hole, producing a bright flare. Instead, almost nothing happened. The cloud survived, largely intact, and continued on its orbit. This was puzzling. Either the cloud is denser than we thought, held together by an embedded star or brown dwarf, or Sagittarius A star's environment is different than we expected. Webb's follow-up observations are helping to resolve this mystery by studying the cloud's composition and the surrounding gas. But what if the cloud wasn't supposed to be consumed? What if it's part of something larger? There's a growing body of evidence that the galactic center is a much more dynamic environment than we thought. Gas is flowing in and out. Stars are forming and dying at an accelerated rate. Magnetic fields are tangled and twisted, and there are structures that defy easy explanation. One such structure is the radio arc, a collection of long, thin filaments of radio emission perpendicular to the galactic plane. No one knows what produces these filaments, but they seem to be associated with magnetic fields threading through the region. Webb's infrared data is revealing that the filaments have counterparts in dust emission, suggesting they're physically real structures, not just projection effects. And the data points to something we didn't want to see. The galactic center might be unstable, not in the sense of an imminent explosion, but in the sense that it's in a delicate balance that could tip at any moment. If a massive gas cloud falls into Sagittarius A star, it could trigger a period of intense accretion, turning the black hole into a quasar, flooding the galactic center with radiation. This has happened before. There's evidence of past outbursts in the structure of the Fermi bubbles and in chemical signatures in nearby stars, and it will happen again. The question is when? Thousands of years from now? Millions? We don't know. But when it does happen, the effects will be catastrophic. The radiation will strip away the atmospheres of planets in the inner galaxy, sterilize star systems, ionize the interstellar medium. Any life within a few thousand light-years of the galactic center would be extinguished. We live approximately 26,000 light-years from the galactic center. We're probably safe. Probably. Now flip it around one more time. Let's talk about the future. Not the far future, but the near future. What Webb will discover next. The telescope is still in its early operational phase. It launched in December 2021, reached its orbit in January 2022, spent months aligning its mirrors and calibrating its instruments, and began science operations in July 2022. As of now, less than 3 years of data have been collected. Webb's mission is designed to last at least 5 years, with fuel reserves for potentially 10 years or more. That means we're only beginning to scratch the surface of what it can reveal. And the data suggests that the most important discoveries are still ahead. One of Webb's primary goals is to find the first stars, the so-called population 3 stars. These would have been massive, metal-free, composed only of hydrogen and helium from the Big Bang. They would have burned hot and bright, lived fast and died young, exploding as supernovae and enriching the interstellar medium with the first heavy elements. No population 3 star has ever been directly observed. They existed too early, too briefly, and their remnants are too faint. But Webb might be able to detect them, either as individual objects at extreme redshift or as collective signatures in the spectra of early galaxies. If we can find even one population 3 star, it would validate decades of theoretical work and open a new window into the universe's infancy. And here's where it turns strange. Some of the early galaxies Webb has detected might contain population 3 stars, but we can't be sure. The spectra are complex, contaminated by dust and emission from later generations of stars, and disentangling the different components is challenging. What we need is a smoking gun, a clear signature that can only come from metal-free stars. One such signature is the HE 21640 angstrom emission line, produced by ionized helium in the atmospheres of very hot stars. Population 3 stars would be hot enough to produce this line, while normal stars are not. Webb has the sensitivity to detect it, if it's there, but so far, no conclusive detection has been made. The search continues, because at the center of this, something waits. Another major goal is to study exoplanet atmospheres in detail. Webb can detect molecules in alien skies that previous telescopes couldn't. Things like methane, ammonia, water vapor, and even potential biosignature gases like oxygen or dimethyl sulfide. But there's a limit to what Webb can do. Its instruments are optimized for infrared light, which means it works best on hot planets, planets that are close to their stars, or that are young and still radiating residual heat from their formation. Earth-like planets, temperate worlds orbiting sun-like stars, are much harder to study because they're cooler and emit less infrared radiation. Webb can detect them if they transit in front of their star, but the signal is faint, and extracting atmospheric signatures requires hours of observation and careful data analysis. And that's assuming the planet has an atmosphere to begin with. One of the sobering lessons from exoplanet science is that not all rocky planets retain atmospheres. Some are stripped by stellar winds, others never had thick atmospheres to begin with. Venus, for instance, has a thick atmosphere, but it's a hellish greenhouse nightmare with surface temperatures hot enough to melt lead. Mars had a thicker atmosphere in the past, but it was gradually lost to space, leaving behind a thin, cold shell. Earth is the exception, not the rule. We have a thick, stable atmosphere because we're at the right distance from the sun, because we have a magnetic field to shield us from the solar wind, and because we have plate tectonics to recycle carbon. How common are planets with all these favorable conditions? We don't know. Webb is helping us find out. But the emptiness isn't the worst part. There's a concept in astrobiology called the Great Filter. The idea is that somewhere between the origin of life and the development of spacefaring civilizations, there's a barrier, a step so difficult that most species fail to pass through it. The Great Filter could be in our past, something we've already overcome, like the transition from single-celled to multicellular life. Or it could be in our future, something that lies ahead, like self-destruction through war or ecological collapse or runaway artificial intelligence. If the Great Filter is in our past, we're lucky. We're one of the rare species that made it through. If it's in our future, we're in danger. And the fact that we haven't detected any signs of alien civilizations, despite decades of searching, suggests the filter is formidable. Webb might help us figure out where the filter is. If Webb detects biosignatures on multiple exoplanets, it would suggest that the origin of life is common, that the filter is not in the early steps but in the later ones. If Webb finds many planets with atmospheres but no biosignatures, it would suggest that habitable conditions are common but life is rare, placing the filter at the origin of life itself. If Webb finds that most rocky planets don't have atmospheres at all, it would suggest that the filter is even earlier in the formation of stable, long-lived planetary systems. Each outcome tells us something about our own prospects. And none of the outcomes are comforting. We thought we were special. The data suggests we might be alone. Now zoom out one final time. Let's talk about the ultimate fate of the universe. Right now, the universe is expanding, and the expansion is accelerating, driven by dark energy. If this acceleration continues, the universe will keep expanding forever, growing colder, emptier, darker. Galaxies will drift apart, beyond each other's cosmic horizons, until each galaxy is isolated in its own island of space. Star formation will slow as gas is consumed and new gas becomes harder to gather. Eventually, the last stars will burn out. White dwarfs will cool to black dwarfs. Neutron stars will fade. Black holes will slowly evaporate through Hawking radiation, a process that takes 10 to the power of 100 years or more, an unimaginable timescale. And then there will be nothing, just darkness and cold and the faint whisper of particles decaying into radiation. This is called the heat death, and it's the most likely fate of the universe according to our current understanding. But there are other possibilities. If dark energy is not constant, if it changes over time, the future could be different. If dark energy weakens, the expansion could slow down, maybe even reverse, leading to a big crunch where the universe collapses back into a singularity. If dark energy strengthens, the expansion could accelerate so much that it rips apart galaxies, then stars, then planets, then atoms themselves, in an event called the Big Rip. Webb's measurements of the expansion rate and the behavior of dark energy across cosmic time will help us figure out which scenario is correct. And the data points to something we didn't want to see. The universe is not just expanding, it's accelerating faster than we thought. The Hubble tension, the discrepancy between different measurements of the expansion rate, suggests that something fundamental is missing from our models. Either dark energy is evolving, changing its strength over time, or there's an additional component we haven't accounted for. Some cosmologists are proposing early dark energy, a field that was significant in the early universe but decayed away, leaving only the late-time dark energy we see today. Others are suggesting modified gravity, that Einstein's equations need correction at cosmological scales. Either way, the implications are profound. If dark energy is evolving, the future is uncertain. We can't predict what will happen billions of years from now because we don't know how dark energy will behave. We thought we knew the ending. We were wrong. There's one more thing we need to address: the philosophical implications of all this. Webb is not just a scientific instrument. It's a mirror, reflecting back to us the limits of our knowledge and the vastness of our ignorance. Every discovery raises more questions than it answers. Every solved mystery reveals deeper mysteries beneath. We thought the universe was comprehensible, that given enough time and effort, we could understand it completely. But the more we learn, the more we realize how much we don't know. Dark matter, dark energy, the early universe, the multiverse, quantum gravity, the origin of life, the fate of the cosmos. All of these are open questions, and some of them may remain open forever, because there are limits to what we can observe. The observable universe has a boundary, the cosmic horizon, beyond which light has not had time to reach us. We can never see past that boundary, no matter how powerful our telescopes become. And even within the observable universe, there are things we can never directly measure. The interior of black holes, the moment of the Big Bang, the other universes in the multiverse, if they exist. These are not technological limitations. They're fundamental, imposed by the structure of space-time itself. We are confined to a finite bubble of knowledge surrounded by an infinite ocean of unknowable truths. And that's terrifying. But it's also beautiful, because it means the universe will always be a mystery. There will always be something new to discover, something unexpected waiting just beyond the edge of our understanding. Webb is showing us that the universe is stranger, larger, more complex than we ever imagined. And that's not a failure of science, it's a triumph. Every question answered, every mystery solved, brings us closer to the truth. And the truth, whatever it may be, is worth pursuing. So here's the takeaway. The James Webb Space Telescope has revealed that the universe is not what we thought it was. The galaxies form too fast. The expansion is accelerating too quickly. There are rogue planets, invisible dark matter, supermassive black holes that shouldn't exist, voids that are too empty, and structures that are too organized. Every observation challenges our models, forces us to question our assumptions, pushes the boundaries of what we think is possible. And we're only at the beginning. Webb has years of observations ahead, and each new image, each new spectrum, will bring us closer to understanding the terrifying scale of the cosmos. But the deepest mystery remains untouched. If the universe is this vast, this complex, this filled with wonders beyond our comprehension, what does that mean for us? We are tiny, insignificant, a brief flicker of consciousness in an uncaring void. And yet, we are also the universe observing itself, the cosmos waking up and asking, "Why am I here?" That question may never have an answer. But the fact that we can ask it, the fact that we can build telescopes and peer into the abyss and try to make sense of it all, that's what makes us human. And in the end, perhaps that's enough. The universe is terrifying in its scale, but it's also beautiful. And as long as we keep looking, keep questioning, keep searching for truth, we are part of something larger than ourselves, something magnificent, something eternal. Look up tonight. The stars are waiting, and so are the answers.